Welcome to a lesson with Dr. Powell. Let's look at an example of integrating a vector field over a surface. Let's let this surface be a plane, and let's take it over this region right here. Okay, so first we need to rewrite this vector field in terms of a differential 2 form to get us set up. So we do that. Now, taking a look at this, realize that we have, let's see, y dy dz, because y and z are orthogonal to x, and we put them in the right order, counterclockwise order. Z and x are orthogonal to y, putting them in the right order. X and y are orthogonal to z, we put them in the right order. Okay, so this is kind of how we begin. It's kind of like a dot product with something here. And we integrate that over a surface. Now we need to rewrite this dz in terms of x and y. And we do that by thinking of z as a function of x and y. So we take its derivative or its gradient. And the derivative is a rule of how to go from run to rise. So if we have a run of dx and dy, a rise, which is the change, the change of the function, the rise in z, is simply dz. So this dot product tells us what dz is. 2dx plus 3dy is equal to dz. Now we can use that and replace our dz's with it to get everything in terms of dx and dy. And we're going to use this wedge area finding operator. So it's an area operator as well as an ordering operator for telling us orientation if we're looking on one side of the surface or another side of the surface. Now, first of all, notice that dy wedge, as this wedge distributes, the area made with dy in itself is just 0. So we're going to ignore this part. And similarly over here, ignore that part. Next, as we distribute, notice that the dy and dx are out of order. So we switch them. Then when we switch, we make it negative. Dx, dy, and similarly here, dy and dx are out of order. Think of this 2 as a scalar. So like with that, y is a scalar, they multiply together here. If you think of this roughly as a cross product for area or calculation or something like that. Here we have a this 3 and 1 come together, but we're going to make it negative because the dy and dx are out of order. Dx dy, and then we get plus 1 dx dy. Now we can factor out the dx dy and just have negative 2y minus 3 plus 1 dy x dy. Now, before we continue, let's just make one quick note. That is, so this is kind of like taking y11 and dotting it with negative 2 dx dy, negative 3 dx dy, and 1 dx dy. And we factor out dx dy as a scalar almost. So it's kind of like we're taking this vector field, and all along as we move along the surface, we're dotting it with this vector, negative 2, negative 3, 1, which actually, let's see, which actually points above the surface. Keep that in mind, especially since this surface, if it viewed, is kind of like has a positive slope in the x and the y directions. So as it comes up, this actually going backwards in x and up in y, it's going to be above the surface. And really, when we view the normal coordinate system, we're viewing from below it. We'll think about this and visualize it more in just a minute, but let's continue on with the calculation. So continuing on, we have negative 2y minus 2 when we take our expression and simplify it, and that we had when we factored out our dx dy. And notice it doesn't matter what order after we factor out the dx dy that we put this in, because we're going to drop the wedge and just integrate over this region however we can. The wedge was only there for the setup to get what the function was that we were integrating. So let's suppose the x, for instance, can go from 0 to 1, and y, what would it go from? It would go from 0 up till this function, which we could say 1 minus x. Okay, and then from there, we take an antiderivative, go from 0 to 1, and integrate. And notice then at this point, we can do a u substitution. We can make u be equal to 1 minus x. Now in that substitution, du is actually equal to negative du. So this really should be a negative. However, we're not going to make it a negative right now at the moment. That's because, or even at all, and that's because our bounds also switch. When x is 0, then u would be 1, and when x is 1, u would be 0. But to switch the bounds back would put another negative on, which would cancel out with the negative here if we switch the bounds back to 0 to 1. So we'll just leave it like this. And so then we get antiderivative, and we go from 0 to 1, and we end up getting negative 4/3. Notice that this is negative. Does that make sense? We're kind of thinking of, well, think just computationally for a minute for what happened. Recall that in our calculation, we were just kind of thinking about a dot product in some sense, where we were taking like y1, 1, and we were dotting it with this, and we were dotting it with an expression right here. So we had negative 2, 3, 1 right here. So -2, -3, and a 1. And let's just think, and this is kind of like so as we moved over the surface, this was like constant, kind of as we moved along with the different x and y coordinates. It's like we're taking this and we're dotting it with that. And dot product is a lot like projection, thinking of how things are. Now our surface, we're looking at the underside of the surface because it's going positively in the x and y direction. So let's just visualize that a little for a minute. So we have the x and the y and the z, and as we're going, we have positively in both directions here. So we're actually viewing it down here. If you look at this as a vector, so and this is actually steeper. This is like let's see, it's like 2 and 3 in different directions going up with different slopes. If you go up just 1 for z and 1 for x, and then just a little bit for y in this region from 0 to 1, we're pointed somewhere kind of on the underside of this. Now this, on the other hand, think about this going in the negative direction for x and the negative direction for y, and then up. We're actually on the opposite side of the surface. And so we're taking a dot product with something, so kind of across the lines, something that's, something that's under, and something that's, let's see, and something that's over. In fact, it's even this vector, it turns out, if you think about flow through a surface, if this vector was along the surface, actually we'd get 0. This, the fun thing about this guy is this guy is actually orthogonal to the surface. You could even see it by looking at the equation of the line or of the plane that we were just dealing with, which is 2x. Z is equal to 2x plus 3y plus 2. And if you think about what's orthogonal to this, I mean, let's see, you think z, and then you put the minus 2x and minus 3y plus z in an equation. You kind of put this on the other side here, so it's equal to 2. So what's orthogonal, you can even see just as the coefficients, -2, -3, 1, which is exactly here. So actually it's orthogonal to the surface, which means that if you're on the other side of the surface and you take a dot product or projection, it should be in the opposite direction. So of course, we should kind of be thinking about getting a negative result, because we're kind of adding up a lot of dot products with a little bit of dx and dy weighted, but all these dot products are negative. As we're taking a vector that's orthogonal, that's headed on the top of the surface, to something that's a little bit below the surface, and taking a dot product throughout the whole thing, and we should end up getting a negative result. Thanks for watching.